All right, so welcome back. So now we will look at the third order kinetics. So for third order kinetics as well, we can have it in three ways. Now the first one is when the three reactants are not the same. In this way, and the second case is when when just two of them are the same. Okay, and we have something like this. Only two of them are the same. In this case, B is the same thing as A. So, and we are going to have 2A plus B to give the product. Okay, so now the third way is when the three of them are the same. So in this case, both B and C are the same and they will also be the same as A. So which will give us 3A to give the product. So these are the three ways we can have our third order kinetics. Now in class, you only do two of them, and they are the first one where all of them are the same, and when just two of them are the same. You won't touch when the three of them are the same. You will not touch that one. So me, I'm going to start with the first one where the three of them are the same. All right, so after that, we are going to look at when just two of them are the same in the next video. Now let's get into that. So we have 3A to give product, and the rate constant will be K sub 3. So we're going to have the differential rate law to be dA over dt to be equal to minus K3A concentration of A raised to power 3. So this is the differential rate law for this. And if you want to find the rate constant, if you want to solve this to have the integral rate law, what you will have to do is just to separate the variables. So you have to separate the variables, and we are going to have the A. We have the A over A to the power of 3 equal minus K3 dt. So just cross multiply and divide. So just separate the variables. Those ones that are having A, put them together, and the t at one side as well. So you're going to end up having this. So now the next thing is to integrate. Now before you integrate, we can have this to be 1 over a raised to power 3 times the A. Okay, because if you have 2 over 4, it is like 1 over 4 times 2. So that's just what I did here. So that will be equal to minus k substitute 3 dt. So the next thing now is to add integral. Now this is actually a raised to power minus 3. Of course, if we have x raised to power minus 2, it is 1 over x squared. X raised to power minus 3 is 1 over x cubed. So the same thing here, 1 over a raised to power 3 is a raised to power minus 3. Alright, so we now have the A equal minus k3 dt. So you still have to add integral to this as well. Now you're differentiating with respect to A, so that means changing A. So it will always start from the lower limit, which is the initial concentration. When the reaction has not started, we have just the initial concentration. Okay, and the time too, we start from 0 when the reaction has not started. Now at a particular time t, after the reaction has started, we have t, maybe 2 seconds, 3 seconds after the reaction, then the initial concentration will have reduced to A, another new concentration that is lesser than the initial concentration, which is the A at time t. Okay, so when it is 0, we have the initial concentration. Then after some times, we have the new concentration, which is lesser than A naught. So you have to integrate this, and don't forget this is like A raised to power n, okay, dA. You understand? Just as we add it the other time, we add for x to the power n dx. So you can see x, x, a, a. So the same thing, this would be x to the power n plus 1 over n plus 1. So the same thing here. Now our n is minus 3. So the answer for this integration is going to be a raised to the power minus 3 plus 1 over minus 3 plus 1. And this is going to be now, we have the limit from the lower limit, which is a naught, to the upper limit, which is a at time t. So this is going to be minus k3 because k3 is a constant integration of dt. And I believe you understand, and I believe you know what the integration of the t will give us. So let's get rid of this. So we're going to continue. We have a raised power minus 2 over minus 2 from a naught, okay, to a raised power, a sub t. Now, what I actually forgot to mention when I was doing the introduction was that we have two types of integration. We can have the definite integral and the indefinite integral. So the indefinite integral is just to integrate, and that's all. So getting this, that's the indefinite integral. But when we are having the lower and the upper limit like this, we have the definite integral. And the way we evaluate that is that let me try and do this for these two so that I can show you together. So this is going to give us t, just t, from 0 to t. So what you just have to do next now is that you put the upper limit into all this answer you get for the integration, the minus when you put just the lower limit as well. So we are going to have a minus 2. Now the a at time t, you substitute it for this a that you got, then over minus 2, then minus the whole expression again when you substitute a naught for this a. So we're now going to have a naught, okay, minus 2, then divided by minus 2 will be equal to minus k3. Then the same thing for this t. So you substitute t for it minus when you substitute 0 for it. So we are now going to have, we're having common denominator, so we can factorize it out. And if you do that, we have 1 over minus 2 in bracket of a sub t minus 2 minus a naught minus 2 equal minus k3t. Of course, t minus 0 will give us 0, and when you multiply, you get that. So, when you still multiply the whole bracket again, you get this minus half times this, and then the same thing here. So, from here you can see, 1 over minus 2 is like minus 1 over 2. Okay, so, and if you do that, minus will cancel minus over here. Okay, minus will cancel minus, and we have this cancel this. So if that happens, we have just 1 over 2. Now this is like 1 over a at time t raised power 2 minus 1 over a naught raised power 2 equal k3t. And this is the integral rate law for third order reaction. And sometimes you might want to find the half-life for this third order reaction. So if you want to do that, at half-life the t will change to t half. And the meaning of half-life is that the initial concentration is half. The concentration left at half-life, concentration at time t. Now the t is now at time half-life, so it will be the half of the initial concentration. So the amount you start with, half of it is the concentration at half-life. So you have to replace these two things in this expression. Now don't forget this one here, this whole expression is the integral rate law. Integral rate law for third order. So if you want to find the half-life from here, so just substitute t for t half and a to what? A naught over 2. We have 1 over 2, 1 over, so this OAT will now become a naught over 2. So we now have a naught over 2 all raised power 2, then minus 1 over a naught raised power 2 equal k3, then t will now become t half. Okay, now we have 1 over 2, 1 over, so this becomes a naught square over 4 because 2 square is 4. Don't forget law of indices. When you have this, it should be a square over b square. So the same thing here. I need to make this bracket to be a little big, you know. All right, the minus 1 over a naught square equal k3 t half. So we have 1 over 2. Now this will become 4 over a naught square minus 1 over a naught square. So you just take the inverse and we have this equal k3 t half. Then we have the same LCM, the same denominator, so we take the LCM, that will be a naught square, then we have 4 minus 1 equal k3 t half. Then we have 1 over 2, 3 over a naught square equal k3 t half. Now to find the half-life, of course, you just make it the subject of the formula, and from there you can have 3 over 2 a naught square equal k3 t half. So then from here we have the half-life of a third order reaction to be 3 over 2k subscript 3 a naught square. So this shows that the half-life of a third order reaction is inversely proportional to the square of the initial concentration. Now, all these you just should know how to derive them, because that's just the point. There's nothing they want to ask here, other than to just to derive it. So you should know how to derive from the beginning to the end. So don't just memorize blindly. Know how it is done. If you're asked to derive for the rate constant, you stop here and you just have to make the rate constant the subject of the formula. And if you want to do that, it's pretty easy. So all you just have to do is to multiply both sides by 1 over t and times 1 over t. T is going to cancel here to make this. So you now have something like k3 equal to, all this side like that. So that's how to just do that one. Not really hard. So that's going to be the end for this tutorial. Thanks for watching, and I'm going to see you in the next video.